Welcome to our channel. I'm your host, and today we're diving into the enigmatic world of dark matter. Imagine everything you see around you, the stars, the planets, the galaxies, even yourself. All of that, all the normal matter accounts for only about 5% of the total mass and energy in the universe. The rest? Well, a significant chunk, about 27%, is this mysterious, invisible substance we call dark matter. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. It's essentially the universe's ultimate ghost. Yet its gravitational influence shapes the cosmos on the grandest scales. Now you might be wondering, if we can't see it, how do we even know it's there? That's the cosmic detective story we're about to unravel. Scientists, through decades of meticulous observation and brilliant deduction, have found compelling evidence for its existence. Evidence that has revolutionized our understanding of astrophysics and cosmology. It's a quest that pushes the boundaries of our knowledge, forcing us to confront the profound unknown that permeates the very fabric of reality. So buckle up, cosmic explorers. Stay tuned as we uncover the top 3 dark matter discoveries that have baffled scientists and expanded our understanding of the universe. We'll journey through colliding galaxies, explore the unexpected spin of stars, and peek into the high-energy collisions happening right here on Earth, all in pursuit of this elusive cosmic component. Get ready to have your mind expanded, because the universe is far stranger and more wonderful than we can often imagine. All right, folks, let's kick things off with one of the most visually striking and compelling pieces of evidence for dark matter, the bullet cluster. Picture this. 2 massive clusters of galaxies, each containing hundreds of galaxies, hurtling through space and eventually colliding. This isn't a gentle fender bender. We're talking about a cataclysmic event that happened about 150 million years ago. A cosmic smash-up of epic proportions, located some 3.7 billion light-years from Earth. It's a natural laboratory for studying the fundamental components of the universe. Now, when these galaxy clusters collide, something fascinating happens. Most of the ordinary matter in these clusters, the stuff we can see, isn't actually in the stars themselves, but in vast clouds of superheated gas, plasma really, that fills the space between the galaxies. This gas is incredibly hot, millions of degrees Celsius, so hot that it shines brightly in X-rays. So when these clusters collide, this gas from each cluster slams into the gas from the other. Think of it like 2 giant clouds of smoke colliding. They interact. They slow each other down. They create shockwaves. Our X-ray telescopes, like NASA's Chandra X-ray Observatory, can see this interacting gas. And what they show is a classic shockwave pattern, with the bulk of the hot gas lagging behind the galaxies themselves. This makes perfect sense. Gas particles interact strongly with each other through electromagnetic forces, creating friction and drag. So the gas clouds from the 2 colliding clusters have merged and slowed down near the center of the collision, forming a distinct bullet-shaped cloud of gas, hence the name bullet cluster. But here's where it gets really interesting. We also have ways to map out where most of the mass is in this colliding system, regardless of whether it's emitting light or X-rays. How do we do that? Through a phenomenon predicted by Einstein's theory of general relativity called gravitational lensing. Massive objects warp the fabric of space-time around them, and light from more distant objects bends as it passes through this warped space-time. By observing how the light from background galaxies is distorted, we can reconstruct the distribution of mass in the foreground. So astronomers pointed their telescopes, including the Hubble Space Telescope, at the bullet cluster, and meticulously mapped out the gravitational lensing. They were essentially weighing the cluster by seeing how much it bent light. And what they found was astonishing. The map of the mass revealed by gravitational lensing did not coincide with the map of the ordinary matter, the hot gas seen in X-rays. Instead, the bulk of the mass was located out ahead of the gas, almost perfectly aligned with the galaxies themselves. Think about that for a moment. The ordinary matter, the gas, got stuck in the middle of the collision, slowed down by its own interactions. But the majority of the gravitational pull, the majority of the mass, sailed right on through the collision, almost as if the gas wasn't even there. The galaxies, being relatively small and compact compared to the vastness of the clusters, also passed through each other with minimal direct collisions. So, the galaxies and the bulk of the mass stayed together, while the intergalactic gas got separated. This separation is the smoking gun for dark matter. If all the mass was ordinary matter, like protons and neutrons, it would be concentrated where the gas is, because that's where most of the ordinary matter resides in galaxy clusters. But it's not. There's a huge discrepancy. The gravitational lensing shows that the mass is predominantly where the galaxies are, but the galaxies themselves don't have nearly enough ordinary matter to account for that much gravity. So what could this invisible mass be? It must be something that doesn't interact strongly with ordinary matter, or with itself, via the electromagnetic force. It interacts primarily, perhaps exclusively, through gravity. And that, my friends, is the very definition of dark matter. The bullet cluster provides a direct observation of dark matter behaving as predicted, passing through ordinary matter and itself with little to no interaction, its presence only betrayed by its gravitational influence. This observation was a game changer. Before the bullet cluster, some theories proposed modifying gravity, modified Newtonian dynamics, or MOND for example, to explain galactic rotation curves without invoking dark matter. However, MOND theories have a very hard time explaining the bullet cluster, where the gravitational field is clearly offset from the distribution of visible matter. Now let's rewind a bit from cataclysmic cluster collisions to something seemingly more serene, yet equally profound in its implications for dark matter: the way galaxies spin. We're talking about galaxy rotation curves, a cornerstone of the dark matter paradigm. And when we talk about galaxy rotation curves, we must talk about the pioneering work of astronomer Vera Rubin. In the 1960s and 70s, Vera Rubin and her colleague Kent Ford studied the orbital speeds of stars in spiral galaxies. Based on Newtonian gravity, you'd expect stars farther from the center to slow down, just like in our solar system, where planets farther from the sun orbit more slowly. Most of the visible mass in a spiral galaxy is concentrated towards the center. So as you move outwards, the gravitational pull should decrease, and orbital speeds should drop off. This is what we call a Keplerian decline. But that's not what Vera Rubin and her team found. They observed that the orbital speeds remained constant or even increased far beyond the visible edge of the starlight. The stars on the outskirts were moving just as fast, if not faster, than stars closer in. This was a profound puzzle. It was as if some unseen mass was providing an extra gravitational tug. If the visible matter was all there was, these fast-moving outer stars should have been flung off into intergalactic space long ago. The galaxies simply weren't massive enough, based on what we could see, to hold on to them. If galaxies were embedded in massive, extended halos of this invisible stuff, then this extra mass could provide the additional gravitational pull needed to keep the outer stars orbiting at high speeds. The flat rotation curves could be perfectly explained if the total mass enclosed within a certain radius continued to increase, even as you moved into regions with very few visible stars. This dark matter halo wouldn't be concentrated at the center like the luminous matter. Instead, it would be much more diffusely spread out, forming a roughly spherical or slightly flattened distribution that envelops the entire visible galaxy. As you move further out, you're enclosing more and more of this dark matter, so the gravitational force doesn't drop off as quickly as you'd expect from the visible components alone. Chapter 3: The Hunt for Phantoms. Peering into the subatomic realm with the LHC and Beyond, we've seen compelling evidence for dark matter from the bullet cluster's cosmic crash and the unexpected dance of stars and galaxies. But astronomers and physicists want to know what it is. What kind of particle makes up this invisible cosmic scaffolding? The hunt moves to colossal machines like the Large Hadron Collider at CERN. The LHC is the world's largest and most powerful particle accelerator. It smashes beams of protons together at nearly the speed of light, recreating conditions similar to those just after the Big Bang. In these collisions, exotic particles can be forged, possibly including dark matter particles. The hope is to catch a glimpse of dark matter particles being created. Dark matter interacts weakly with ordinary matter, so it won't light up the detectors directly. Scientists look for missing energy or momentum. If the energy and momentum don't add up, it implies something invisible carried away that missing energy. That something could be a dark matter particle. This is an incredibly challenging task. So far, the LHC hasn't definitively discovered a dark matter particle. The absence of a clear signal has allowed physicists to rule out many theoretical models for dark matter. But the LHC isn't the only game in town. There's a multi-pronged approach. Besides collider detection, There's also direct detection and indirect detection. Direct detection experiments aim to observe dark matter particles interacting with atomic nuclei in detectors deep underground. These experiments are marvels of engineering using superpure noble liquids or crystals. They are buried deep underground to shield from cosmic rays and background radiation. Experiments like Lux Zeppelin, Xenont, and Pandax are pushing sensitivity to unprecedented levels. They've set stringent limits on the interaction cross-section of WIMPs with ordinary matter. And there you have it, a glimpse into the shadowy realm of dark matter through the lens of three pivotal areas of discovery: the dramatic separation of mass and light in the bullet cluster, the stubbornly flat rotation curves of galaxies pioneered by Vera Rubin, and the ongoing high-tech hunt for dark matter particles at the LHC and other sophisticated experiments worldwide. Each of these threads weaves into a compelling tapestry of evidence, pointing to a universe far more mysterious and mass-dominated by the unseen than by the familiar. The quest to understand dark matter is more than just an academic exercise. It's a fundamental inquiry into the nature of reality itself. What is this stuff that sculpts galaxies, binds clusters, and dictates the ultimate fate of the cosmos? Answering this question will not only fill a huge gap in our cosmic inventory, but will also likely unveil new particles, new forces, and perhaps even new dimensions of space and time. The journey is challenging, the path uncertain, but the potential rewards for our understanding are immeasurable. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating insights into the universe. Let us know in the comments what other cosmic mysteries you'd like us to explore next. Keep looking up, keep questioning, because the universe is full of wonders waiting to be discovered, and the story of dark matter is far from over. The next breakthrough could be just around the cosmic corner.